Hello everyone, this video is about the depletion width of a PN junction. Suppose we have a PN junction. And we know that there is a contact interface between the p-type material and the n-type material. And in the p regions, the majority carriers should be holes. And in the N region, the majority carriers should be electrons. And the whole concentration is represented by Na. The electrons concentration in the N region should be represented by Nd, where Nd stands for the concentration of donor atoms. Na stands for the concentrations of the acceptor atoms. At the interface, where x is equal to 0, the electrons in the N region would somehow jump across the border into the P region because of the concentration difference. So, do that. So as a result, the N region itself is originally neutral, but because of the transfer of electrons right at the interface, the in the neighborhood of the contact interface, the N regions end up losing electrons. Losing electrons means losing negative charge. As a result of the loss of the negative charge, we have surplus positive ions right across the next to the contact interface. On the other hand, in the P regions, there is surplus negative charge right at the interface. So in other words, in the contact interface, there is an electric field because of this charge imbalance. The electric field in this scenario is pointing leftwards. And as a result of the imbalance charges right at the contact interface, we have a region of imbalance charge. And this region is so-called depletion layer. Depletion region. And suppose the horizontal axis is x. And if I'm going to draw the charge distribution of this PN junction, the charge outside the depletion region should be 0. 0 means neutral. But at the border of the depletion region, then the charge abruptly increase. Just like in this case, we have the division layer at xn for the N region, and we have a boundary of the division region in the P region, and the boundary is minus xp, so minus xp xn, and the charge distribution right at xn we have a certain step increase. And the trash here is Q and D, and then the XN, okay? So for exactly the same reason, we have surplus negative charge in the P region. The amount of trash is, according to this diagram, Q and then NA and then XP. And do not forget that you also need uh, to look at the cross-sectional area as well. So the area here should be A. So you have to multiply the whole expression by A, where A stands for the cross-sectional area. The because of the conservation, the law of conservation, due to the conservation of charges, we expect the area in here to be exactly equal to the area in the N region. And accordingly, we have this equation. And xp should be minus. So we have xp in times n. So if you summarize this formula, you should end up with xn divided by xp being equal to na divided by nd. Now, you have the imbalance charge distribution here. On the left side of the contact interface, we have the P region, and the charge that you have just next to the contact interface is this amount. And on the opposite side of the contact interface, you have another amount of charge represented by this area, and the charge here is positive. So in this case, you should be able to work out the electric field by Gauss's law. If we draw a Gaussian boundary, Gaussian enclosure here, there should not be any electric field from here up to the boundary of the division layer. And for exactly the same reason, the electric field will be zero until it reaches the border in the N side. So what we are going to do is to draw the electric field. Suppose the vertical axis is the electric field. Suppose the horizontal axis is x, and At the N region, the border is xn, and in the P region, the border of the division layer is minus xp. And by observation, the electric field starting from here should be zero, and the electric field will increase in intensity until it reaches the middle where the electric field becomes maximum. So I expect the electric field I expect the electric field to be linear. Yeah, if you integrate this area, then you have the electric field here, and you have another electric field here by integrating the area here until it reaches zero. So the electric field for this portion of the curve of the line is E, and then Q N A, and then X plus XP divided by epsilon. And in here, the electric field is given by Q and D. Maybe there is a negative here. Anyway, X minus Xn and divided by epsilon. And we are looking at the maximum. The maximum is where x is 0. According to this diagram, according to this equation, E max should be equals to this expression with x is equals to 0. So I can get QNA xp divided by epsilon. And according to this equation, the electric field here is equal to this amount. And when x is 0, we have Q and D and then xn. Maybe there's a negative side here. No, yeah, both sides are positive. Now, the next thing that we are going to do is to work out the junction voltage. The junction voltage should be calculated by integral and the electric field integrating the electric field from minus xp to xn. Integrates the electric field against x, and that's all. And then now, the integral expression looks difficult. We don't know how to start with. But then the electric field E of x can be calculated from these two formulas. But if you want to just integrate the electric field from this point to this point, we just need to work out the area of this triangle. According to my high school knowledge of geometry, the area of triangles is given by the base times the height divided by 2. The base here is xn plus xp. And the height here is Emax, but Emax is given by tail and A xp divided by epsilon. And do not forget that you have to divide the whole expression by 2 because you are looking for the area of this triangle. And according to the right hand side of this equation, then it is also equal to Pn xn x of n plus x of p times Q n d xn and then 2 epsilon. And I'm going to do that. Now, let's move this portion of the expression to the opposite side. Move it. So we have equation 1 here, and we have equation 2 here, and we do it. 2, and then epsilon, and divided by Q. The left side and the right side is xn plus xp times xp. And I'm going to explain the left side, the expression on the right side. And this one is going to be and by the same token, I can also do the same for this equation. So we end up with J, epsilon, and Q. Maybe I leave out something. And A, and this is N D. And let's continue, yeah? Xn, so Xn plus Xp times Xn. So we have Xn squared plus Xn Xp. So we have 2 more equations. And we will only focus on equation 3 and 4. And right now we are now nearly finished. If you add equation 3 to 4, the left side become 2vj epsilon divided by q. And then 1 over NA plus 1 over ND. But the right side of the equation is, if we add them together, yeah, this, yeah, we will have x plus xp squared. And xn plus xp is just the division layer, the thickness of the division layer. So we can quickly, conclude from this equation here. The value of xn plus xp squared is equal to this amount. Xn plus xp is the width of the division layer. So we can just simplify the expression on the right. So this is the final formula, and this is the division B. And if you have any question, please leave your questions to the comments box, and I will try to answer your questions if I have time. Thank you very much for your attending these lectures, and I hope you enjoy it. Thank you.